Dear ladies and gentlemen, today I'd like to introduce to you the Pourbaix diagram of the elements and the position of their electrochemical potentials with respect to the different reference electrodes potential which are used in practice. So, very well known as the standard hydrogen electrode potential with a set to 0 volt at all pH values. This is indicated here with the blue line. Another even well-known reference electrode is the silver chloride or the saturated calomel electrode, here indicated with a green line. Both are independent from pH and they are a little more positive with respect to the standard hydrogen electrode. Another quite different reference electrode is the reversible hydrogen electrode with the trade name Hydroflex from our company. This electrode is dependent from the pH value, and you can see here at the pH 0 it is identical with the standard hydrogen electrode, of course. So, if you look now, for example, for an electrochemical reaction from palladium to palladium hydroxide, indicated here with a yellow line, and you measure this potential in different solutions with different pH values, you will get different values if you are using the standard hydrogen electrode, and you are getting different values if you are using the silver chloride or calomel electrode. This is because the palladium potential is pH dependent and the reference electrodes are not. It is totally different if you are measuring with the reversible hydrogen electrode, as you can see here with the red arrows. In that case, you get the same value at any pH. So, in fact, this is a more practical reference electrode than the both others. So, just come back to the standard hydrogen electrode. It consists out of a platinum sheet which is immersed into a hydrochloric solution with a pH value of 0. And of course you have to purge hydrogen gas to the platinum sheet. The silver chloride electrode consists out of a silver sheet which is immersed into a solution with potassium chloride ions. By definition, the hydrogen potential has no temperature effect. That means if there are different temperatures, all the influence is dotted to the other reference electrodes or other conversions. That means the silver chloride potential is temperature dependent. If you bring now both electrodes into a beaker with a solution and you open the electrodes with the diaphragm, so you have an ionic contact in between, then you can measure a voltage between the standard hydrogen electrode and the silver chloride. So in fact you could now observe the values given in literature, but be careful because we have now still the liquid junction potential at the bottom side of the electrodes at the diaphragm. This liquid junction potential depends very much on the mobility and concentration of the ions in the solution. A total different approach is if you are using the reversible hydrogen electrode, which you are immersed directly into the measuring solution, the same solution as your sample. This is a reversible hydrogen electrode. Again, this has no temperature effect, has no pH effect, and has no liquid junction potential. So, again, this is a very practical reference electrode. Here on that slide, you will see in the middle how our hydrogen reference electrode Hydroflex looks like. At the top, you have a hydrogen source which has enough hydrogen for 1 year. If you turn on this hydrogen production with a wrench, the electrode will fill during 24 hours completely with hydrogen, and now you can measure your electrochemical potentials. So, thanks a lot for your attention, and good luck with our reference electrodes.